Thank you very much for the introduction, Dominique, and thank you all for staying for so late. And I will be discussing a little bit on the edge singularities, which are associated with a 3D elastic solution, and the computation of the so-called edge stress intensity functions. It is not 100% related to finite fracture mechanics, but since we have V notches and we have the need to compute the generalized stress intensity factors in 2D and in 3D, it becomes much more complex. And we have been studying this 3D elastic domain for quite a while, and I thought it would be of interest to discuss it a little bit. Now, since we are not having this summer school in Madeira, I wanted to show you a little bit what is it in Tel Aviv. So we are in Tel Aviv, and that's how Tel Aviv looks like. And there aren't that many people on the beach because of the coronavirus, but still people are around. And we have Tel Aviv and we have Jaffa, and you can see here Israel. And this is where Tel Aviv is located along the Mediterranean Sea. And in Tel Aviv, in the city of Tel Aviv, there is a university which is called the Tel Aviv University. And you can see the building, and I would say that this is how it looks like right now because there are not that many people around. I'm not there, I'm at home at the moment. And in that building, we have two labs. One of them is the computation mechanics laboratory, where you can see it over here. And we also have a biomechanics laboratory for experimental thing, where we do also experiments on V notches and structures which tend to fail. So after I explained a little bit on where is it that we are located, I will tell you what is the content of this talk. So we will be discussing the singular solution, and we will be looking at 3D edge singularities. And although these methods are applicable for non-isotropic problems, I will stick to the isotropic problems because these are difficult enough to explain. And I will start with a simple problem, which is the Laplace equation, which is the elliptic equation, just to give you the methodology. And then after I will present this methodology, I will go on, and after I will present how the solution looks like, I will show a method to compute this stress intensity functions by what is being called and baptized as the quasi-dual function method. And after these two things, I will show some numerical examples to demonstrate how these methods can be used in practice. So I will start with things that most of you know, and these are the two-dimensional solutions. So as you can see here, we have a domain, and let us suppose that we have a V notch, and we will use either the Cartesian coordinate system, x1, x2, sometimes I will call that x and y, and also a polar coordinate system, which is r and theta, and omega will be usually the solid angle. So what is it that we usually want to solve? Usually we want to solve the partial differential equation. So for example, here we are talking about the Laplace equation just for simplicity. I promise I will go to elasticity and you will see the equations in elasticity later on. So we want to solve the 2D Laplace equation, for example, for the field U, which is a function of x and y. It is easier to represent U as a function of r and theta. And therefore, the Laplace equation in terms of the coordinates r and theta is shown in here. And this is the problem that we want to solve in the domain. And we are looking at a case at which we have homogeneous boundary conditions on these lines which intersect at our singular point in here. So we either discuss on a Dirichlet boundary condition or displacements boundary condition when we will be talking about elasticity, or the derivative, the normal derivative, which equals to 0, which will be equivalent to the traction-free boundary conditions when we will discuss elasticity. So what is it that we know about the solution of this equation in the vicinity of this singular point? So we know about what we really know is that we can decompose the solution into an infinite series, which would look like a function, a factor, a, times r to the power of lambda, times another function, which is a function of theta. So we can do a separation of variables. And then if we plug that in the equation here, we get simply an ordinary differential equation because r will drop out. And we can solve this differential equation. You can see it's a differential equation only in phi of theta, and we can compute that. It's a very simple solution. So we get that these phis are either sine lambda I of theta or cosine lambda I of theta. Now notice that this lambda I, which we will call later on an eigenvalue, these ones can be either positive or negative from the mathematical point of view. It doesn't mean that I need to have only positive numbers. I can also have negative numbers, and still I will be able to solve this equation, which means also the negative numbers will satisfy the Laplace equation. These lambdas are determined by the boundary conditions. So once I have the solution r to the lambda I phi I of theta multiplied by a factor, I can then go and try to satisfy the boundary conditions. And when I will try to satisfy the boundary conditions, then I will determine these lambda i's so that I don't obtain only a trivial solution, which is u equals to 0. And I will have an infinite number of these lambda i's. And for each lambda I will have the phi i's, which are either sine or cosine functions. So if I want to summarize, I may speak about a differential equation. And if k12 is 0, then I get the Laplace, and k11 equals to k22, I will get back the Laplace equation. This is a little bit more general equation. You see, I have also a term which is a differentiation with x and y. But anyhow, if I solve this equation, the analytical solution will be an infinite sum of these eigenvalues and eigenfunctions, and I will also have the negative ones. Again, this is a proper solution for that equation in general. Now, what happens if this represents, for example, temperature? So the Laplace equation can represent physically a temperature field. If I would consider these terms, I will get, when r goes to 0, I will get an infinite temperature field at these points here. Therefore, we say that from the physical point of view, these terms cannot serve as a solution of a physical phenomenon. Therefore, we throw that away. Mathematically speaking, we say that these functions over here do not belong to the H1 norm, the Sobolev norm. Therefore, they are an admissible solution for such a problem. But from the mathematical point of view, these ones would solve this equation. So I split the solution into two. The admissible solution, which will be u, is a function. It's an infinite sum of eigenpairs, so it's eigenvalues and eigenfunctions, plus there is a dual solution which satisfies the equation, but I don't consider that a solution, so I call that a dual solution. Now, I also would like, please, to ask if there are any questions during my talk. Please don't hesitate to interrupt me, and I will be glad to answer, because that will make the presentation more like a discussion. Now, these are well-known things. In a fracture mechanics, for example, when this angle is such a one that it's a 360 degrees, then we have a crack. And for a crack, we have these lambda i's to be 0, 1/2, 1, 3/2, 2, and so on. We have an infinite number of terms. In fracture mechanics, we say that since the term with r to the 1/2 is the most singular, because when you look at the stresses, this would tend to infinity, whereas all the others will be finite or tend to 0, then we look only on the first terms with lambda I, which is equal to 1/2. For the Laplace equation, or the scalar equation, as you can see it here, the first eigenvalue, if we have traction-free or Neumann boundary condition, will be 0. The second one will be 1/2 for a crack. The third one will be 1, and so on. If we have a 90-degree, we will have the first one, which will be 2/3, 1, then we will have 1 and 1/3, and so on. So once we know how the solution looks like in 2D, let's talk about how do we compute. I will go back here. How do we compute these coefficients? Because so far we know how to compute these terms here, but we did not yet discuss how we compute these coefficients. We don't know how to compute these coefficients because so far we were only interested in solving the equation in the domain, and we only fulfilled the boundary condition in the vicinity of the singular point, but we did not say anything about the boundary conditions away from this singular point. These coefficients will be determined by the boundary conditions away from the singular point, and in elasticity we call them usually the first 3 of them. In 3D elasticity we call them the first 3 stress intensity factors. So how do we compute these stress intensity factors, which are of real interest to us? There are many methods. So one of the methods is the J integral. The other method is what we call the path-independent integral. Some people call that the contour integral method, and the others call that the dual function method. And to use this method, we really need the dual solution. It's not only that we need the primal solution, we also need the dual solution. The dual solution is this solution with the eigenvalues which are negative. So first of all, let me introduce a path-independent integral, which is a very important integral, because we want to use it not that very close to the singular point, because usually we don't have an analytic solution. We solve the problem by finite elements. And we know that finite element solutions in the vicinity of this vertex here, or tip here, the finite element solution is of very low accuracy. So we want to use finite element solution as far away as possible from this vertex. Therefore, it is important to use an integral where we can go away from this singular point here. And by having such an integral, which is a path-independent integral, I can go away from the singular point, and this integral would provide me the same value as if I would go very close to that point here. So if I have a solution, which I call that U, it's a solution of the Laplace equation, for example, and I have a dual solution, which I call that W, then this integral can be shown to be path independent. Not only that it is path independent, it also has a very, very interesting property. If I take an eigensolution I, for example, which is associated with alpha, with lambda 1, and here I take W, which is associated with a dual eigensolution, then if this W does not correspond to the same eigenvalue as this U, then I will get a 0. This is what delta ij stands for. Now, as we said, U is an infinite series. So if I will plug here not only one of the eigen pairs, but I will plug in here the entire solution U, I will have an infinite number of eigenpairs. But because of this fact, if I would like to extract, for example, A1, which is associated with K1, the stress intensity factor, then I take here the infinite sum, but I choose here the dual solution associated with lambda 1. And then when I will plug it here, because of the orthogonality, this term will be orthogonal to all the terms in the sum except one of them, which is the same index. If I want to get A1, I will plug here the dual solution associated with lambda 1, and then I will get only A1. This is shown in these two expressions. So if I take the dual solution of phi I, psi I, and here I take all of them, which will be associated with phi 1, phi 2, and so on, I will only get A1. Namely, what I have to do is compute this integral wherever I want along a path over here. So what is it that I take from the finite element analysis? I take the solution, I take the gradient of the solution along that path, and you see here the solution again, and I compute that integral with the dual solution for which I am interested in that specific coefficient. So for example, if I will be interested in A1, I will take the dual solution associated with lambda 1. And when I will plug in here this term, I plug it here, I will get exactly A1 having this B1 taken as a given a number. It's simply a number. So from the practical point of view, all I have to do is take the finite element solution along a path, and the path can be a circular one for convenience. Take the derivative of the finite element solution, plug them in this integral, compute that integral, and the result would be this coefficient for which I'm interested in. And I can compute each and every one of them independent of the other, because each time I will choose a different dual solution here, I will get a different coefficient here. And that's the way, a very simple and very accurate method for us to extract stress intensity factors for the Laplace equation, and then we can do that for the elasticity equation. Now, I explained what happens in 2D. Now, what would happen if we would like to find a solution that will be a solution in 3D? How would the solution in 3D be different than that solution in 2D, which we already know that exists? So let us demonstrate how is the procedure to get that solution. And when we will demonstrate how the procedure is, I can explain what are the difficulties in 3D compared to 2D. So let us assume again that this solution, which you see here, is an eigensolution for the 2D problem. So there is a coefficient r to the lambda I, phi I of theta, and as I said before, I can compute each and every term here that I would like. So now I ask myself, what does this solution what is it that it satisfies? It satisfies the 2D Laplacian. So if I plug that in the 2D Laplacian, I will get that this equals to 0 because this is the 2D solution. Now let us look how would the 3D operator would look like. So it is exactly the 2D operator, plus we have another term, which is the second derivative with respect to the third coordinate. So again, if you look here, I have x1 and I have x2, and this x3 is the coordinate along this. Now in 3D, it's not anymore a point, it's a line. So I'm interested in a solution along that line. And for the moment, I will stay away from the vertices. So this is a 3D vertex, which is the intersection of the crack with the free surface. So I have x1, x2, x3, and the Laplacian in 3D will have the Laplacian in 2D plus this term. So I would say, let us try and have a separation of variables. We have this function of theta. we look for a solution which is r to the lambda I, and let us suppose that the entire behavior in the 3 dimension will be into this function here. In 2D it was a factor. Now, because we have a 3D, then this becomes a function along the crack front. So I ask myself, could that be a solution for the 3D problem? So I take this one, I plug in here in the operator. Now I know that since this one is independent of r and theta, I can take it out here. So I get here again the operator which operates on r to the lambda I phi I of theta. And I know that this satisfies the equation. So that would become 0. So I have the 3D Laplacian operating on such a solution. This will be 0. But then I have another term which is left over here. And this is the second derivative of this function times r to the lambda I times phi I of theta. But this is not 0 because we cannot expect that this function here will be a constant. Only if this function here will be a constant, then I will get a 0. But if this would be a constant, it will mean I have a 2D solution. But I'm looking for a 3D solution. So this is not 0. I see that the leftover is the second derivative of that function, r to the lambda I. So I ask myself now, if I add to the 2D solution with this function here, if I would add another term with a minus, that when I will plug it in, it will eliminate this term here. Maybe when I take the solution to be the sum of these two, maybe then when I will plug them in, I will be able to satisfy the equation that it will become 0. So I take this expression, I put that in the 3D equation, in the 3D operator, I apply the operator on this solution, and then I find out that what comes out, it's not a 0, but I get a term now which is the fourth derivative of this function, and you can see that r now has a power of lambda I plus 2 from here. And I say, okay, I notice that when I take two terms in my solution, namely I take this term and this term, the remainder is the fourth order already, and I increase the power of r to the lambda I by 2. So now I ask myself, maybe I add not only the first and the second term, let us add a third term, and maybe this term will eliminate that. And indeed, if I take this term and I plug that in the equation, I will eliminate the remainder, which is this one, but I will be left with a remainder which will be the sixth derivative, and here I will have lambda I plus 4. So I can continue infinitely to add terms. And when I add more and more terms, I find out that I get a solution, which is the two-dimensional solution, which you see it here, only that AI now is not any longer a factor, but a function. It is a function along the crack front. And in addition to this one, I have an infinite number of terms, but each time I add a term, I see I add the derivative of this function here, and ri to the lambda I increases each time by 2. This is what happens if I'm looking at the Laplace equation. So if I am looking at a more complex equation, so it's not really Laplace, otherwise I will not have k12, k13, and k23. This equation is a second order elliptic equation. And if I'm looking at this kind of equations, and I'm trying to find out what will be the solution for such a type of equation, I will get this term here. I hope you are able to see that because the letters are not that large. But what is important to realize here, that again, I have the solution. And of course, to each positive eigenvalue, I can get also a negative eigenvalue, which is a solution. So I again divide that into 2. I have the dual solution, and I have the solution itself. And now, what is it that is important about the solution? For each eigenvalue, lambda I will have an infinite number of functions associated with it. So we call these functions which are associated with the two-dimensional solution, we call these shadows, like someone who's walking in the sun, and then there are a lot of shadows because of this person who's walking. So because of this two-dimensional solution here, I have shadows here, which are associated with the two-dimensional solution. And now the three-dimensional solution will not be only an infinite sum of the eigenvalues. Each eigenvalue will have also an infinite number of terms associated with the two-dimensional eigenvalue. And this complicates considerably the methods that we use in order to extract these functions now. And these are, in elasticity, these will be the stress intensity functions along the edge. And if I have a two-dimensional solution, then these functions are not any longer a function of the third component, the third axis z. They will become constant. And if these are indeed constants, and we are at a two-dimensional case, then this is a constant. Then this term remains, and all the term and all the series hereafter, all the shadows would be eliminated because I will have here derivatives. If you remember, when we looked at the Laplace equation, we said we have the first term, which is associated with 2D, and then we have the second derivative, and then the fourth derivative, and so on. So we have derivatives which jump by 2 for the Laplace equation, but once we have a term which is also a derivative with respect not to d square z, but to dz, I will have also first derivative. So for the Laplacian, I will have only this term, then this term, and then the one with the fourth. But for a general problem like this one, I will have also the first derivative. Why is it important to speak about it right now? Because when we go to elasticity, we will see that always we have the first derivative. Only for the Laplace equations, we do not have the second derivative. Okay, what is the formal way, the mathematical formal way to obtain the 3D solution? So the formal way to do that is to take the operator, which you see it here, that's a general operator for a scalar problem in 2D. So again, if k11 equals to k22, and k33 equals 0, k12, k13, and k23 equals to 0, you would get back the two-dimensional Laplace equation. If k11 equals k22 equals k33, and all the other are 0, then you get the Laplacian in 3D. But this one is usually the general term of a second order partial differential equation, which is elliptic. So we take this operator and we split that into 3. So we take all the terms which have only derivative in x and y. These are associated with the 2D solution. So this m0 for that problem will be k11 second derivative with respect of x. Then it will be k22 second derivative with respect to y. And it will be twice k12, the second derivative of u, with respect to x and y. So this is the operator, which is the 2D operator. Then we ask ourselves, what is the operator which is left, which has only one derivative with respect to z? And here we find these two terms here. So we'll have 2k13, the second derivative, the first derivative with respect to x, plus 2k23 first derivative with respect to y. This is m1, and this is multiplied by dz. So multiplied by the first derivative with respect to z. And here we are left only with another operator, m2 we call that. And if you look here, this is only the second derivative with respect to z, and this is only k33. So we split our operator into 3, and then if we do that, we find a set of equations to compute all the shadows associated with a given eigenvalue. Why is it? Because when we will take the sum, the solution, which is the sum, and we will plug that into this operator, we will find out that a of x3 multiplies this operator, and this is exactly the 2D operator. And then if we find phi 0 and lambda, we can plug them in here. We have this term, we move that to the right-hand side, and now we have an equation to compute the first shadow. Once we have the first shadow and phi 0, we can plug them here and find phi 2. If we have phi 2, we plug it here with phi 1, and we have phi 3, and so we can compute all the series that we would like. I will show an example, for example, that will explain that. So let us look at this differential equation. For this case, k13, k23 equals 0, k33 equals 1. Then the operator here is simply m0, which is the 2D operator, plus dz squared. So if I want to find a solution, m0 is here. I find the two-dimensional solution. I don't have m1, so this goes away. And only I have here this equation, which I find it here. And if I have phi 0, I will find phi 2. If I find phi 2, I will plug in here, I will find phi 4, and so on and so forth. And I can compute the entire three-dimensional solution, which are the shadow functions. Let us look at a real example. So let us look at a domain with 270 degrees. It's a V-notch. And when I look at that, I can look for the Laplace equation. And what you see here, it's from 0 to 270. And you can see here f0, which is phi 0, and psi 0. It's the dual. So the primal and the dual for the Laplace equations are the same. But if I look at the second case, again, 90 degrees. But here you see this operator is not really the Laplace operator. It also have derivative of u with respect to x and y. Then what is it that you find out? That phi 0, which is the solution itself, it's the purple line here, whereas the dual function associated with it, with the negative term, is the almost yellow line here. And now if I look at phi 2 and psi 2, so that's the first shadow, again for the Laplace equation, they are the same. But if you're looking at the second case here, you will find out that they are different. So we are able to find the primal solution, the dual solution. We can do the same for a problem which has which is a crack, and you can see here the solutions again. For the Laplace equation, they are the same, the primal and the dual solution, whereas for the other case, they are not the same. Another issue which is important for us when we would like to go and compute these functions. And now we need a function along the crack front. It's not a factor anymore. When we would like to compute these functions, we want to make sure that there is a normalization between the primal and the dual functions. And we can normalize that. And I don't want to go into the details because it's just a technicality. So we can normalize it, and there is a normalization factor. And if we look at the same problem and we normalize them, you can find out, for example, if you look at for the second case here, when you look at phi 0 and psi 0, so it is this line and this line, you can find out that psi 0 is by far smaller than phi 0, so that under this integral, we get a normalization which equals to 1. Okay, so now we are able to show that we can compute the singular solution in the vicinity of an edge. That's the edge here. And it has this form. So for each eigenvalue, there is an infinite number of shadows. And the question is, how do we compare this A1 of Z, A2 of Z, A3 of Z, any one which we would like? Again, these functions and the shadows are only dependent on the angle, material properties, and boundary condition in the vicinity of the crack front. And what I will call edge, these are edge flux intensity functions, these ones are still to be computed by taking the boundary condition away from that singular edge. And somehow we have to compute them. And one of the methods that we want to apply is similar to the contour integral method, the dual function method. I would like to now in 3D, instead of using a one-dimensional curve, now I need to use a cylinder. And I would like to be able to compute data on the surface of the cylinder. And I also don't want to come close to that edge because I need data from the finite element solution. And again, I don't want to come close to this edge. Now, there are methods in the literature that propose ways to compute this stress intensity function along the line. But usually it's not a function. Usually people say, okay, let's take a cut, a perpendicular cut, and think that it is a 2D domain. And along this 2D domain, I will compute the data at that point, which is of interest. Now, if someone would like to do that, they would find out that because of these shadows, every path 2D independent integral is not any longer path independent in 3D. So if one would like to use the J integral in 3D over a plane, they will realize that this J integral would depend on the radius. And as they go further away from the edge, the function, what they would compute, they will find out that it depends on R. So if one needs to compute the stress intensity factors or functions along this edge, yes, then they really need to come very, very, very close to that edge, which means they will need a very, very, very fine mesh in order to resolve the singularity here. Otherwise, they will get a lot of numerical errors. So we want now to go ahead and extend the contour integral method so that we would be able to go away from that edge here and still be able to have something which is close to path independency. We will not get there, but we want to come very close. So with a work together with Professor Monique Doge and Martin Costabel, who are in Rennes, we worked for quite a while. It took us about 2 or 3 years to come up with a new integral, which is called the quasi-dual function integral. And now we want to apply the same methods, but now we can not only take one term, which is associated with the negative value of the function here, which we would like to compute. In order for us to apply an integral over a cylindrical surface quite far away from that crack front, we don't need only to take the first term. We also need to take the first shadow, the second shadow, the third shadow, and so on up to the mth shadow of the dual solution. So we can find the two-dimensional dual eigenpair, but we have also to compute as many as we wish shadows. And if we use m shadows, the more shadows we use, the better we can come to a integral which is almost path independent. Why is it? Because when we compute this integral, again, over this surface, the more terms will be taken here, the higher the m will be here. You see m here? The more you take, the the higher will be the m. We always have a reminder in this integral, and the reminder is r to the power of lambda 1 minus lambda I plus m plus 1. So if we don't take any shadow, m will be equal to 0. So if we want to compute the first so-called flux intensity factor here, then I will end up with lambda 1 minus lambda 1, which will be 0, plus m, which is 0, plus 1. Therefore, the remainder here will be of an order of r. So if I want to compute something, it will change as a function of r as I go away. Now, let us suppose that I take m equal to 4. If m will be equal to 4, then I will have here a remainder which will be of an order of r to the power of 4 plus 1, then it will be r to the power of 5. Now, if I have r which is smaller than 1, let's say 0.1, if I don't include these terms, I will have here an error of an order of 0.1 to the power of 1, it will be 0.1. If I take here n equal 4, I will have 0.1 to the power of 5, which is much, much, much smaller, the remainder. So this is the important issue that we really need to know about the dual, the 2D solution, the 2D dual, but we also have to compute the shadows. And if I take as many shadows as I want, I can control this remainder of the integral so that it will become insignificant, since I know at which r I want to extract my solution. Therefore, I can choose what m I should put here, so this remainder will be close to 0. And this allows me to move away from this edge. I don't really need many, many refinements here, so I can really move away, take many shadows, plug them in here in order to compute this integral here, and this integral here equals this a, which I'm interested in, times another b, which I did not yet discuss. So this b is coming in here into play. So this becomes a little bit complex. So I will go ahead and try to explain how do we choose these b's. From the practical point of view, let me go back. From the practical point of view, I need to compute this integral. It's an integral over a cylindrical surface. This is the traction operator on U. This is the dual solution, which I know. This is the U, which is the finite element solution of the specific problem. And this is the traction operator over this dual thing, which I know. And I have to compute that from a finite element solution. So what the method is, we use Gauss integration, and we compute from the finite element analysis. We take the finite element analysis along a cylindrical surface. We take the traction of it. We take the finite element solution itself. And we have this dual solution here. And we can compute this integral. So once we have this integral, the question is, how do we compute the function? The function, it's a function. It's not a number. So let me go 2 slides back and explain that again here. I'm able to compute this term, which is here, and an integral gives you simply a number. So I will have a number here. But this number has to represent, for me, a function. I want to find the function a of z. But all I know that on the right-hand side, I don't have a function. I have an integral of a function which I don't know and I need to find, times a function which I can choose, but this is an integral, therefore I will get here a number. But again, I don't want the number, I want a function. I want a of a function of z. So how do I do it so that I retrieve really the function? And the method is the following. Let us assume that a can be expanded in polynomials. And let us assume that the polynomials that I will choose are very, very specific ones, are the Jacobi polynomials. So this is Jacobi polynomial of order 0, of order 1. So this is like a constant. This is something to have to do with x3. Then it will be x3 squared up to a polynomial of degree p. If I can compute a0, a1 up to ap, these are numbers. Each one of them is a number. Therefore, I can generate for myself a function a, which is a function, not any longer a number. It's a function because I have all these numbers. So how do I get these numbers? For this, I go back and I remind you that I have to specify what is this b. I will go back. You remember I said I have to take here a b, which I choose. It's my choice of b, because this b would determine for me the dual solution. I can put here any function which I want. So if I can put any function which I want, I can generate the function in such a way that it will also be constructed of these Jacobi polynomials. And why did I choose the Jacobi polynomials? Because they are orthogonal. So if I take the Jacobi polynomial of order k under an integral with Jacobi polynomial of order j, then I get a delta jk. So if each time I choose a different b, so for example, I choose here k1, I will get a1. If I choose here k0, I will get a0. So this is what I am doing. I am computing from the finite element solution this integral. But each time that I compute this integral, I use a different b. If I use a different b, I will get a different coefficient a. So if I do a finite element solution, I get the displacements, I get the stresses along this surface. I plug them in here into this integral with a specific b, and this will give me the specific a here. So if I take b, which is j0, I will get a0. If I do this integral again with j1, I will get a1. And I can continue and do that, and I get as many terms in the representation of this function a of x3. So if I compute that up to p, I can do that adaptively. I can then ask myself, is this a good enough approximation? If not, I simply compute another term, and I ask myself how this additional term of a polynomial of degree p plus 1 now, how does it improve what I already have? And I can do that adaptively and choose as many of these as I want, so that this will not change any further. And you can have here the methodology and some numerical examples on how does it work. Now, I don't have much time. I have 40 slides, and I'm coming to the 3D elasticity. So I showed a method by which we can compute the 3D solution. We can plug it in a quasi-dual function method and compute not only a pointwise value of the stress intensity along this line, but I can compute a function along this line. So how does it generates in order to go to 3D elasticity? The difference between the Laplace equation and 3D elasticity is that the set of equations is a little bit more complex, well, maybe much more complex, and you have to solve 3 partial differential equations at a time. So these are the so-called Navier-Lamé system of linear elasticity in terms of the displacements, UR, U theta, and UZ, which are the 3 displacements which we are looking for. And we want to solve this equation in the vicinity of this line here, which is the edge. And again, I'm not talking on the vertices, because there the solution changes. But I move a little bit from the vertices, and I say I want to compute the stress intensity functions along this line. Again, what we do, we split the operator, and we split that into 3. Again, m0, m1 times dz, and m2 times dz squared. And since I know what happens for the Laplace equation, I go and I say the same thing. Let us take an infinite number of terms for each 2D eigenfunction. Then there will be also an infinite number of shadows. This is how m0, m1, and m2 looks like for the elasticity system. And if I'm looking at m0 times phi0, now it's a vector, right? It has three terms, one for u r, one for u theta, and one for u z, associated with the first eigenvalue. This is precisely the 2D equation, but this is precisely the 2D equation for plane strain, which means that in 3D, there is no plane stress situation near a vertex. And this is a very big misconception. People say, okay, let's think about something which is very, very thin. But if you want to think about something which is very, very thin, you have the influence of the vertices. And you cannot compute in 3D really a plane stress situation in the middle. So there is no notion of plane stress if you talk about 3D problems and vertices and edges. So this is the precise 2D equation for plane strain. And if I can compute that one, I then can compute the first shadow, and then I have a recursive formula to compute the second shadow, the third shadow, the fourth shadow, and so on. How do we compute the first shadow? We insert the 2D plane strain equation into this m0 times phi0. You get three ordinary differential equations for phi0, phi0 of r, phi0 of theta, and phi0 of 3, which is phi0 of z. You have three equations for the three functions, and it is very easy to compute. Then you substitute phi0 into this equation, and then you find phi1, and then you can go forward and find phi2, and so on, and you can build all the solution for the three-dimensional equation. The ordinary differential equations which come to hand, I wrote them here in order if someone of you would like to really solve these ones. And we have done that. And let us look at the structure of the 3D solution in elasticity. So in elasticity, if, for example, we are looking at the first eigenvalue, then what you see here in blue is the two-dimensional solution. So in two dimensions, you have the u, so-called ur and u theta, which are a function of theta times r to the power of alpha 1. Now I switch to alpha because in elasticity, we have the Lamé constants, which are lambda, so they may interfere. And this is what we refer to as mode 2. So this is associated with K1. This is associated with K2. This is associated with K3, and so on. But for each one of these, we have an infinite shadows. Now, infinite number of shadows. The first shadow is associated with the derivative of the stress intensity function. The second shadow is associated with the second derivative of the shadow of the edge stress intensity factor. And you can see that they become less and less singular, because if this will be 1/2, for example, for a crack, then the next term here will be 3/2, and the next term here will be 5/2, and so on. But we have now the entire structure of the solution in terms of 3D. And if you want to see exactly how it looks like for a crack, for example, you have it given here. The black things are exactly the 2D solutions. Now, this is A4 because we have 3 r to the 0. Here we have 3 r to the 1/2. These are the displacements. The red term here is what is referred to as the T stress. You see it's r to the 1. If you take the derivative of that, you get a constant. The blue terms, you see there are an infinite number of some are the shadows. And the green ones, which you see here, are simply the rigid body motions. So this is how the solution would look like in the vicinity of a straight edge. These are the stresses associated with these displacements. And I was talking about A4, A5, A6, but A4 is associated with K1. This is the engineering terminology, just multiplication by material properties. A5 is associated with K2, and A6 is associated with K3. And this is the two-dimensional solution, but for each two-dimensional solution, you will have an infinite number of terms. And of course, you can see here in blue, in red, you can see here the t-stress. So I will skip some of the slides. I just want to show you some examples. I don't want to go and prove to you that the theorems work properly. One of the examples that I think is interesting is the compact tension specimen, which is being used mainly in experiments to compute, not to compute, to determine K1C. So if you look in the standards, the domain is given as a 2D domain, and there are numbers which are given how you should compute K1C depending on the load that is applied here at the instance of fracture. If one does the 3D analysis and looks what is K1 as a function of the dimension, so we go from -1 to 1, from -1 here to 1 here, it looks as if it has such a very, very curved shape. But notice it is going from 160 to 200, and still we have from 0 to 160. If we want to look at exactly how it looks like in the real scale, first of all, we have to look what the standard says about how one should compute K1C. So if we take P, for example, we normalize P over B omega, so we take P100, these numbers, we get K1C, which will be in 2D. If you would compute this problem as a 2D problem, you see K1 is close to 180. Now, if we look at the 3D solution, you see it over here. This is the 2D solution, the red line here. And the 3D solution, you can see it up here. You can see that it gets almost to 200 in the middle. And it's a little bit lower at the ends. And if you look at these numbers here and you look at this shape of the stress intensity function along the straight line here, you can see this shape here. And indeed, if you really look at a 3D case, experimental data, you can really see that there is this front which is really not straight, because in the middle, the stress intensity is higher than at these points. And you really see the shape, and the difference here can be up to 10%. So this is to say that when one uses three-dimensional entities, one should be very careful when interpreting them into a 2D setting. And the next question would be, what happens if there is a slight deviation from the straight line by 10 degrees? So now we are talking about a slanted crack, which is 10 degrees. Then you can see that previously you had K1C was this. Now you can see that you have here a big difference, up to 200 here, when you have a small slant. And these computations can be done very, very easily once we are using these methods. So I come to an end. Most of the things that I have been discussing are described in this book, which came out in 2012, and I already found quite a number of typos, and then I will have to correct them. But what I would like to say that we can provide an explicit representation of the displacement and stress field in the vicinity of an edge. We can propose a hierarchical extraction for the edge stress intensity functions. It is very efficient, and we don't really need to have a refined mesh in the vicinity of this edge. And you have to keep in mind, this is something which is very important that I would like to emphasize, that methods which work well in 2D and are path independent, they do not become path independent any longer in 3D. And if one wants to use them, they should use them with cautious. Namely, they have to go very, very close to the singular edge. And as a future, it's not future, it's already in the past, but to what I presented now, we have extended this quasi-dual function method to anisotropic and multi-material interfaces where we have composite materials, and then we have complex eigenpairs. The exact solution for cracks now, which are not, I was talking about a straight front. So we extended that to circular fronts, any boundary condition, it does not have to be axisymmetric or whatever, and also elliptical cracks, which are very, very common in practice. So that brings me to an end, and I thank you very much for the attention. And if there are any questions, I will be more than glad to answer.